So, in our last class we were solving shortest path problems. Now, we will continue from there. Very quickly, in our last lecture we have seen the Bellman's optimality principle, that if we have reached a particular point, no matter how we have reached, the remaining distances should be optimally found, right. So, that is the essential idea, and based on which we have an algorithm called Dijkstra's algorithm. Now, this is how the official statement of the Dijkstra's algorithm, let us note it down. First of all, assign a level 0 to the starting node S and all other nodes a level infinity. Make S a permanent node. Let P equal to S, where P is the last node made permanent. That is the step 1. At the step 2, dpk be the distance from node P to all other non-permanent nodes k. Recompute Lk, means the level of all the remaining nodes, as minimum of Lk, the current level, and Lp plus dpk, right. So, that is step 2. Step 3, if the ending node T is made permanent, then stop. Lt is the shortest path from S to T, is alright, else go to step 2, otherwise keep computing. So, idea is that all the nodes should be made permanent. When all the nodes are permanent, then the Dijkstra's algorithm really stops, right. Now, let us look at one more problem. So, this is a network, then we have these distances S to A and A to C, etc., and we have to find, let us say, the shortest path between S and T. Really, you see, like here you are having the network shown. Many a time it is not always that network will be drawn for you, right. Basically, all you have is a matrix, something like a distance matrix, that S, A, B, all the nodes on one side and the other nodes on the other side, and the distances between them, that is the matrix that will be available to you, right. So, if we have to follow the Dijkstra's algorithm, how do we go about? So, if you look at it, that we create the distance matrix. So, here is the distance matrix, this side is the nodes, that side is also the nodes, and S to A, S to B, S to D, and if you see the node S to node A is 20 and node A to node S is also 20, then this particular all the rows, the first row and first column, second row and second column, they will be identical. But if the distance from S to A or A to S are different, then we have different rows and column values. So, anyhow, this is the distance matrix we obtained first. Now, after the distance matrix is obtained, you see, first we have made S permanent, right. S is made permanent and a temporary level is assigned to S as 0, then A, B, C, D, T, all the remaining nodes, they are assigned as infinity as the your temporary level. Now, is anything as permanent? Now, S is made permanent. So, this is yes, and this arrow means that this is the last node that is to have been made permanent, and made from, I mean nothing, because after all S has to be made from S, but we need not write it, right. So, that is the first step. Now, what we should do? Please think. I have already shown one example in our last lecture. So, what should you do? From S, what are the points you can reach? You can reach A, D and B. There are direct paths. Where direct path is not there, we consider the distance to be infinity, and since infinity as a level is already there, we need not compute them. So, what will be the new level of A? You see, it should be the lower of current level of A, which is infinity, then 0 plus, because level of S is 0, last node to have made permanent, plus the distance. So, 0 plus 20 is 20. So, 20 is lower of 20 and infinity. So, level of A should be now 20 instead of infinity. How much should be B? B should be then 55 and D should be 75. So, exactly that is what is done here, that 0, 20, 55 and 75. Now, which one should be made permanent? You have to make out of all the nodes. See, 0 is already taken out because it is already permanent. Out of the remaining nodes, which one is the minimum? A is the minimum. So, then it is optimal distance from S to A will be 20, and then we make A as also permanent. So, A is made permanent, and A is made permanent from whom? From S. So, that made from is noted also. Clear? So, S and A are now permanent. A is the last node to have made permanent, right? A is the now made permanent from node S. So, A is the last node to have made permanent. So, now the next distances are to be computed from A. So, A you see we can reach two nodes C and D. So, if you go to C, then it should be 20 plus 82, 102, but current value is infinity. So, which one is lower? 102. So, we can have a value of 102 now. But what about D? The D value was 75, and if you go from A to D, A value is 20. So, it will become 112. So, no point exploring that path, 75 should remain. So, that is what is shown here, that here 75 has remained and C becomes 102. So, look, we have recomputed C as 102, T still remains infinity. Last node to have made permanent was A, and through which we have computed all these values, and out of the remaining values, because these two are already permanent, now 55 is the lowest. So, we make it permanent. So, now B is made permanent. So, now S and B they are made permanent, and this is also made from how the B, look here, we computed currently. So, this mistake people make sometimes. So, at this time we have made D and C permanent. So, you may be thinking that one of them should be now D and C we have recomputed. So, one of them should be made permanent. No, it should be the global minimum out of all the remaining nodes. So, that is where the dynamic programming comes up, right. So, it is not that the recent calculated values only should be made permanent. Out of all the remaining nodes, see S and A were already permanent. Out of all the remaining nodes, that node should be made permanent. Which one is the lowest possible level? So, since the level of B was 55, so B is made permanent. Got the point? So, at the next round the B is made permanent. So, again we recompute all the values. So, you see from B you can reach C, you can reach D, and you can read T. You cannot reach T. So, if you reach C, the value is 55 plus 71, which is higher than 102. If you reach D, again that value is higher than 75. So, at this point when B is made permanent and last node to have made permanent is B, we have no recomputation, right. The values that were available they stay. But out of the remaining 3, now D becomes permanent, because D is the value which is 75. So, now D is also made from C S, not C S. So, therefore, now which one is lowest? So, D. So, D should be made permanent now. So, at this round we have made D also as the permanent node, right. So, actually at this round D was made permanent. After D is made permanent, we again calculate at D, you see we can compute T as 150 and C we do not change. So, out of 102 and 150, since 75 is also there not permanent. So, at this point 75, sorry, 75 was the last node to have made permanent. So, we make 102, that is C, as permanent, right. Proceeding like this, at the last step, here we see that this value was 150, but from C the distance is lower. So, we make at this point 137, because the value of C was 102 and now T will become 137. So, T is now made permanent and we have completed, all the nodes are now having permanent level. Is it all right? Sometimes if you really want only S to T distance, if other nodes are not permanent, but T is permanent, S is permanent, we can get the distance from S to T if that is all that we want, right. So, now this is our complete table. These are the labels which are no more temporary, they are all permanent. If all the labels are permanent and made from list is also available. So, what we do? T is made permanent from C, C is made permanent from A is made permanent from S. So, S to A to C to T, that is the shortest path and that distance is 137, right. So, that is Dijkstra's algorithm explained to you once more time. What I said, that when there are negative distances, then we have the Bellman-Ford algorithm. This algorithm is nothing but an extension of Dijkstra's algorithm, but only difference is that we cannot make any of the nodes permanent. Is it all right? So, it is like an exploratory process. All the nodes has to be used for recomputations of the levels. So, at every round keep computing the the what you call the values again and again until you get a situation that no further levels are changing. So, we will not discuss that in detail, but just remember, when negative distances are involved, one requirement is there should not be a loop which has a total negative distance. And second thing, we cannot make any of the nodes permanent. So, all the nodes are candidates for calculation at all the rounds. So, that is the difference. But we discuss now what is known as the Floyd's algorithm. The Floyd's algorithm, essentially the idea is to by this method, using a matrix method, we can find out the shortest path from any node to any other node, right. So, that is the algorithm known as the Floyd's algorithm. How do we do that? So, let us take this particular shortest path problem, where there are 1, 2, 3, 4, 5 nodes and these are the distances. So, we need to find out the shortest path from any node to any other node. How do we proceed? So, we make two matrices. The first matrices is called the distance matrix and the second matrix is called the root matrix. The distance matrix is the distances like infinity, a to a and they are all infinity, x to m there is no such path. So, it is also infinity, L to and then like m to x, look, no path from m to x. So, infinity, right. So, this is called the distance matrix, and in this distance matrix this is symmetrical in the sense that because up and down both distances are same, but it need not be. You can also take distances if a to m and m to a are different, right. Now, root matrix is a matrix which is very simple. Simply take 1 1 1 1 2 2 2 3 3 3 3 3 and 4, all 4 and all 5, right, all 1s, all 2s, all 3s, all 4s and all 5. So, simply take it. Now, for convention, although the node names are A, M, L, B and X, we call them as 1, 2, 3, 4, 5 also at some time. Just remember, A is 1, M is 2, L is 3, B is 4, X is 5. Now, why they are not named as 1, 2, 3, 4, 5 in the beginning? Because it will confuse you otherwise. because here also 1 and here also 1. So, we will not be clear, but anyhow just remember that. So, this is the first round. At this second round, what we do? We highlight the first column and the first row, right. We have highlighted the first column and the first row, and here this column. So, what is we do now? We try to find out the distances through A, right. All the distances we are now finding through A. So, M to X, what is the distance through A? B to L, what is the distance through A? See, B to L current distance is 19. What is the distance from B to L through A? You see, A to L is 10 and B to A is infinity. So, B to L through A is infinity. Out of infinity and 19, which one is lower? 19. So, we keep 19. But B to A, what is the current distance from A to B? Infinity. What is the distance of B to A through A? There is no path. So, we do not put any change, we remain it, keep it infinity. What is the current distance from M to X? M to X or X to M is infinity. What is the distance from M to X through A? Through A, the distance is 23 and 18. You see, through A, the distance, because A is now highlighted. So, M to X through A will be 23 plus 18, that is 41. Look here also, M to A is 23, A to X is 18. So, 23 plus 18 is 41. So, very simply you simply look at the corresponding row and corresponding column and row, and M to X is 23 plus 18. Yeah. So, this is 23 plus 18, that will be 41, right. So, that is how we proceed in this particular situation. So, look at this now, M to M, M to M through A. You see, M to M through A will be 46. Why? Because 23 plus 23 is 46, right. So, look at this, this is currently 10, it should be how much? Because 23 plus 10 is 33, more than 10. So, it remains at 10. Now, look at this value is currently, you know, it was infinity, but 23 plus 18 is 41. So, it will now become 41. But every time you change, you see, like here we have changed it to 46. So, we change it to 1. Here we have changed it to 41, and that is through 1, that is point A. So, we write 1 here. Got the point? So, that is why it is called root matrix. That means, M to X is 41 through 1, right. That is the meaning of 1. So, now that we have made all computations from A to M, you know, we leave it here and we call it now this, you see the other side also, this is 10 to 10 20, and this also changes. So, through 1. So, all the values we look at. So, this infinity will be 41 also. So, nothing changes in the 4th row, because none of the items, and in the 5th row you see this 41, it was infinity, now it becomes 41 and 36, and they are through 1. So, now we have computed and we get these two matrices, which we can call D1 and R1. D1 is the distance matrix, R1 is the root matrix. How we have observed this? We have now got the original distances or all distances through 1, that is through A. Through the point A, all distances are computed, and all those values that has been changed, they are now changed to 1, right. So, this is my new distance matrix, and we have got but all that thing through 1. So, this is the D1, right. Now, after we have got D1, now we highlighted 2. What is the point 2? That is M. So, we highlight the rows and columns of M, and here look at the column M, right. So, now look at what will be changing. This infinity will become 46, this 10, can it be 33? No, this infinity will now become 58. How? Let us look at what is the distance from A to B is infinity. Same thing is B to A. Now, if you go through M, what will be that distance? That distance will be 23 plus 48, that is 71, because go to A to M and M to B, it will be 71. So, this infinity will now become 71, right. So, we can now compute all such distances. What about A to L? Do not change. So, you see, keep doing it. 23 plus 23, 23 plus 48, 23 plus 41, 41 plus 41, 82, but current value is 36, 48 plus 10, current value is 19, 48 plus 48, 96. So, this infinity will become 96. So, like this we change. So, you see these 4 values change at D1 and R1 through L, and we get these changes in the matrix. So, look here, these values were 1 1 4 4, we have now changed them to 2 2 2 2. So, we have now got our new matrices, that is D1 and R1. That means, through 1 the values are obtained. Then what do we do? Logically, you see, and where do we stop? We started at D0 and R0. Through all these distances we have computed now D1 and R1, and finally, we have reached D2 and R2 matrix, right. 1 was through A and 2 is through M, right. So, we have now obtained both D2 and R2. So, both these matrices are now obtained. So, after obtaining both D2 and R2 matrix, next it should be the third point. What is the third point? That is point B. So, that means row and column of this third point, that is B, sorry, the third point was L, that should be highlighted. So, L now should be highlighted. So, L is highlighted. Now, look what are some values that will change. These 46 will be 20, right. These 46 also will become 20. These 48 will now become 29. These 41 will now become 17. So, can you see lot of changes? Through L, lot of distances are changing. This 96 will become 38. This 26 no change. This 36 will now become 14. So, lot of changes will now take place through L, because the distances are smaller, right. So, exactly we have made all these changes, as we said, look at 7 plus 7 14, 19 plus 19 38, then 19 plus 10 29, 19 plus 10 29, and all these changes will be now reflected in putting in this matrix 3 at the appropriate places, right. So, once again, how do we get D3 and R3 from D2 and R2? Basically, the L is the third point. So, all the distances are to be recomputed by taking this row and this column, and wherever the values are lower, we replace them. So, what exactly is happening? What is Floyd's algorithm? The Floyd's algorithm, if you really understand carefully, it is nothing but the application of Dijkstra's algorithm in a matrix form, right. Earlier we were applying Dijkstra's algorithm between only 2 points in a linear one dimensional situation. Here we are using for a 2 dimensional situation, and if we go from D0 R0 to D5 and R5, all possible combinations are explored. So, that is the essential idea of Floyd's algorithm, right. So, we have obtained now D2 and R2, and from there D3 and R3. So, the 3 points are explored. What will be our fourth point? The fourth point is B. right. So, fourth point is B. Now, look at, now B is highlighted. Can you identify some points, some values that will be changing at this time? Just identify 29 plus 29, 29 plus 29, 19 plus 19, 19 plus 20. Just think over. Are you getting anything which is changing here? Let us see the result. We got nothing, right? No item could be changed because all the values through B, the values are higher. Like M2x, look at M2x, it was 17, but if you go through B, it will become 68. So, we do not change. So, we do not change anything. So, we get what is known as D4 and R4. So, now we come to our last point, that is point number 5, that is X, right. So, we highlighted the rows and the columns and here that particular column. So, now tell me, can you find any change? Look at all the distances, 17 plus 17. What about this 20? See, 7 plus 7, 14, it will change, right. 48 does not change, 37, 37, 24, 34, 34, 24. So, not much changing, but maybe some changes would be there. So, actually only one value is changing. So, that is this becomes, earlier it was 20 through 1, now it will become 14, right. So, that now completes our matrix. So, we have got this D5 and R5, right. So, let us look at how to read this particular matrix. Suppose we need a distance from B to L, B to L. So, B to L is distance is showing as 19. So, shortest distance is the direct path, that is 19, and through point number 3. So, B to L, and L is the third point. So, basically it is just through L only, B to L through point number L, right, that is all. So, another distance, what is the distance from A to B? A to B is 29 and it is through point number 3, that is M. Sorry, what is the point number 3? That is L. So, A to B, the shortest distance is A to L and L to B, right. So, you can study this, and while doing that, please solve this problem also, right. Please solve this problem also. We have 5 points, 1, 2, 3, 4, 5, and these are the distances. Use Floyd's algorithm, starts with D0 and R0, and use this method in a suitable manner and come out with the distances. For your reference, I am giving the answer here. This is the answer. Now, if you look at the answer, one interesting thing will be found out, which was not found in the previous example. What is the shortest path from 1 to 5? Look, 1 to 5, the shortest path is 77, right. 1 to 5, 77. How? Through 2. Through 2. But if I see through 2, I find 1 to 2 is 30, but what is the shortest path 2 to 5? So, we have to look at 2 to 5 also. So, 2 to 5 is 47 and that is through 4. So, you have to read like this. See, 1 to 5 shortest path is 77, it is through 2. Then we have to see 2 to 5 also. 2 to 5 shortest distance is 47 and it is through 4. So, therefore, 1 to 5 shortest distance is 1 to 2, 2 to 4, 4 to 5. Is it all right? So, that is exactly how you can work out Floyd's algorithm, and we have really studied 3 important algorithms, Dijkstra's algorithm, Floyd's algorithm, and although I did not say, but I just mentioned the Bellman-Ford algorithm for negative distances, right. So, thank you very much, and that concludes our network portion.